Yeah, so we are going to have a look at how to integrate trigonometric functions. You see that's what we are going to learn about today. And our starting point will be first to lay down the basics, what we need to know when it comes to integration of trigonometric functions. And then after all the basics have been laid down, then we're going to see how we can build up from these basics to try and integrate some complicated situations. So that's what we're going to be focusing on in this lesson. You see. So when it comes to the integration of trig functions, there are two results that form the basis foundation. You see that. So like before we go anyway, it's good to actually just lay down some preliminary material that you should know before you embark on this journey of learning how to integrate trigonometric functions. And one of the things that you must know, the preliminary work is trigonometric identities. Like, so there are these identities that you need to know. Cos squared x plus sine squared x is equals to 1. And then 2, also you have to know that 1 plus tan squared x is equals to sec squared x. Then 3, you also have to know this one that cos squared x minus sine squared x is equals to, there are three versions of this one. So this is just cos 2x. And this is also the same thing as saying 1 minus 2 sine squared x. And also 2 cos squared x minus 1. So these are some identities that you should know. And then the fourth identity that you should know is the one that goes as follows. It says that cos squared, sorry, not cos squared 2, but it says that cos 2, let me use x, says cos squared x is actually equal to half to bracket 1 plus cos 2x. And then also you must know that sine squared x is actually equal to half to bracket 1 minus cos 2x. So these results that we have just, we call them the uh, half angle identities most of the time. So they are very important for integration. So they are one of the most important results. So these results, uh, which we refer to as the quadratic identities, and the ones that we have stated here, number last, they are the identities that you will actually require quite often whenever you're dealing with challenging integral problems. You see that? So these ones that I've stated, number 3, actually, they are the ones we use to actually derive these two identities that you have here. So even if you know these or don't know, it's fine, but it's good just to raise them up. But for integration, we won't need much of them. And then the last thing that you have to know also when it comes to integration of trig function 5 is expansions of sine x plus or minus y and cos x plus or minus y. So every time when you have to do the integration of trigonometric functions, this is the preliminary content. You must always know these identities. So once you're aware of all these identities, then your life will be much easier when it comes to integrating things, you see. So you're going to see how all this is going to be featured as we go about different problems. But now, since we have laid down the preliminary work, it's now time to start talking about was talking about more of how to integrate trigonometric function. Then when it comes we need to have the following basic results for integrating trigonometric functions. So we want to look at some basic result. So the first basic result is the one that talks about how to integrate a function like uh, sine theta. So let's say you want to find the integral of sine, then maybe let's say alpha x dx. This is equal to minus 1 over alpha cos alpha x plus k. You see that? So this is the result that you have to know. So this result, I call it the recipe because it is actually an information statement which tells you how to actually go about integrating trigonometric functions like sine theta. So if you are to look thoroughly into this given result, you will see that actually that these things suggest steps by which someone has to follow every time when you are trying to integrate trigonometric functions, and what steps are being discussed here. So every time when you want to integrate a trigonometric function like this one, the first step that you start is you start with number one inside here. You see that? So first you differentiate the argument. So we refer to that thing there. So the input of any trigonometric function, we call it the argument. So your step number one, it starts there like that. Then your step number two, it follows the result that you get from one. What you do is you take it out as a reciprocal. You see that? So two, take out the result as a reciprocal, like that. So your result number two is this thing that you get, because when you integrate, when you differentiate here, you get alpha. So that alpha that you get, you take it out as a reciprocal, and then you obtain that. Then number three, the third step is you should know. So what you should know that that if you integrate sine of x without anything involved, then this thing is just negative of cos x plus c. You see that? So whenever you integrate sine x, then you should always know that this is the case. So this result that we stated here is what we use now to bring this term here. That's why you see that there is a minus here. The minus here is because of that minus that we see there. And then we have that function cos appearing because every time when you integrate sine, you get that. So the third step is more like just integrating the trig function itself. You see that? So that's your step three. So integrate the given trig function using this result, like that. So this is how things will operate every time when you're integrating trigonometric functions. So simple basic trig functions are integrated by following these results. So we're going to demonstrate these by looking at examples, but now it's good for us to just state them down before we learn how to use them. Then there is the other one, which also works in a similar way, the one for cos. See that? So what you should know is that if you want to integrate cos of alpha x dx, then this is just 1 over alpha sine alpha x, then plus k, like that. So we still have the same kind of information. It's just that now the integral of sine of cos is actually sine. So here what you just have to pay attention to is that the integral of cos x dx is just sine x plus c, like that. You see. So these are the results that you need every time when you're integrating trigonometric functions. So what we need now is to see how to apply these in problem solving. You see that? You have to be careful about that. But one thing also that you have to be careful of is that you must pay attention there. You see that? So you must pay attention there. The argument must be linear all the time. You see that? So the argument must be linear. So when your argument is not something which is linear, quadratic, cubic, then these results don't work because most students, they don't pay attention to the details of the given recipes. They just assume that this is the case and they generalize it and apply it in instances where it's not supposed to be applied. So you must be careful that every time when you apply these kind of results, you only apply them where they hold true. So they only hold true when the argument of the given trigonometric function is a linear function. If it's not linear, now we have to resort to other tools. We don't have to do this. You see. Okay, so now that we have seen, let's look at examples. So some typical examples that one can get can be something like this. So you can be given the following example where they say evaluate I, the integral of sine 5x minus 1 dx, and then 2, the integral of cos half x plus 3 dx, like that. So you can be given that, and then they say, can you deal with that? So how do we deal with such information? So to deal with such information, this is how we proceed. So solution. So for I, so every time when you want to evaluate an integral, you can give it a name at first. So you can say let I equal to the integral of sine of 5x minus 1 dx. Then now you begin the step. So remember, step number one, every time when you're dealing with integration is you start here. So that's your starting point. So what you do is you differentiate the argument. So when you differentiate the argument, it's more like finding dx of 5x minus 1. So when you differentiate the argument, 1 will become 0, but when you differentiate 5x, you get 5. So that result that you get, what you do is you take it out, but when it comes out as a reciprocal, so you get 1 over 5. Then now after that, you differentiate the trig function itself. So now you look, what is the derivative of sine? So the derivative of sine is actually cos. So you'll get cos of the same argument, which is 5x minus 1, then plus k, like that. So this is how things work most of the time. See, so this is how things work when you're integrating these trig functions. And then we want to integrate the next one. So again, I'll give it a name. I'll say let I be the integral of cos of half x plus 3 dx. So what do we get here? So what we get here is, first thing, we differentiate the interior or the argument. When you differentiate inside here, you will get half. When you take half as a reciprocal, it becomes 2. And then now we come and differentiate. Sorry, when you integrate sine, you get minus cos. So here it's supposed to be minus anyway. Then when you integrate cos, you get sine. So this is going to be sine of half x plus 3, then plus k, like that. So these are things that you should know, that every time when you're integrating basic trig functions, you simply treat them like that. Start with the argument, take out, integrate the function, put the pieces together, and then add the integral constant, you see. So this guy here, we didn't explain, but every time when you're performing this type of integrations, we refer to that as an integral constant. So I'm not gonna, I think we did explain in our first section, lesson discussion, why we actually need an integral constant. So now we know why it has to be there, so we don't need to re-emphasize on that. You just have to remember that every time when you're performing an integral without limits, then definitely you have to introduce the integral constant after the end, like that. So this is how we integrate basic trigonometric function. But we know that basic stuff, we don't usually encounter that in exam. So it's time now to move to material that can be a bit challenging in this discussion. So now what we want to look at is integrating even powers of cos x and sin x. Now we want to learn how to integrate even powers of cos x and sin x. We want to deal with even powers of cos x and sin x. That is, how to integrate these trigonometric functions when they are raised to powers like 2, 4, 6, 8, or any even number to think of. So these are the questions. This is where actually when things start to get tense. Though it's very easy if you pay attention as what we're going to be doing here, because once you master whatever we're going to explain here, this is going to be the easiest integration ever. So now let's see how to deal with this one. So how do we deal with even powers? You see that? So when integrating, when integrating even powers, we make use of half angle identities. You see that? So every time when you're dealing with these things, this is what you need. You need the fact that cos squared x is the same as half 1 plus cos 2x. And then also you need the identity which says cos sin squared x is half to 1 minus cos 2x. So every time when you're dealing with even powers of cos and sine, then these are your tools. These are your go-to guys. They are the things that will allow you to solve any problem that you will need to know. So what we want now is to train ourselves how to actually apply these things to solve our problems. So now let's look at examples. So let's look at examples which we can use for practicing this. So a typical example that might be given might be as follows. So they will say evaluate the integral of what? So they will say evaluate the integral. Let's start with the sine, small easy things. Let's say sine to the power 4x dx, and then b the integral of cos to the power 6x dx. So they will say, can you deal with that? So how do we deal with the integral of these sort of functions? So to deal with integral of this sort of function, this is how we proceed. You see, so at first you can let I be the given integral, which is sine to 4x dx. Then the procedure is always as follows. So every time when we are dealing with even powers of either sine theta or cosine of theta, or cosine or sine of x or cosine of x following what we have here, then the first thing is you have to first break down the given function into powers of 2. So when you take this, you will get sine squared x dot sine squared x then dx. So that's your starting point. You check those even powers and you break them into simple powers of 2. Then for each power of 2 factor that you have, you make a substitution using the half angle identity. So you know that according to the half angle identity, this is the same as saying half of 1 minus cos 2x dot, again, there's another half 1 minus cos 2x, then dx, like that. Then these two halves, they are multiplying, so they multiply and give a quarter. We can pull them out of the integral and you remain with a quarter. Then I will have these two similar brackets, which will give me 1 minus cos 2x all squared dx. But now I can expand that bracket easily. What will I get? So a quarter is still sitting outside. So now I expand. When I expand, I get 1 minus 2 cos 2x plus cos squared 2x then dx. Then dx. So if you look closely, you will see that this guy we can integrate perfectly. This guy we have just learned, but this guy still has a power. So we need further fixing here, because this thing is still in a power of 2. Because our laws that we have learned, they don't deal with powers. They need these Q's just to be power 1 only for us. So which means for that cos squared 2x, I have to find also a suitable identity. But how will I create an identity? So to create an identity for that, I go back to my half angle. And what do you realize? You will see that this thing here, it says every time when you have x here, you have 2x here. So what you're going to do now is, instead of having x, you're going to take this x and you're going to swap it with 2x. So when you do that, what does it imply? It means you're going to have cos squared x is equal to what? So you're going to have 1 plus cos. So whatever there is x, you are putting 2x now. So there you're going to get 4x like that. So that was going to be the same thing even if you did it with sine. So it means you're going to have half 1 minus cos 4x like that. So which means we have seen now that if I want to deal with this term, I have to replace it with that one. So we go and replace it there again. And what do we get? So it means now if we apply what we have just seen, we're going to have a quarter of the 1 minus 2 cos 4x, or 2x, sorry, then plus half bracket 1 plus cos 4x, then dx, like that. Then I simplify. So if you look here, this guy that is sitting here and this guy that is here, these are like terms. You see that? So those guys are like terms. So what I do is I take and add them together. And what does it give me? So it gives us a quarter integral of 1 plus half is going to give us 3 over 2, then minus 2 cos 2x, then plus half cos 4x, then all these dx, like that. So now what we do now is we start integrating. So each factor now is integrated. So 1/4 is going to wait for the outcome. So first thing we start with 3 over 2. So you know that when you integrate a constant, you just multiply it with the integral variable. So you just get 3 over 2x. Then we come this side. So now we have a trig identity. So remember a trig identity, first thing is you start by differentiating here and you start by differentiating there. So when we do that, when I differentiate here, I'll get 2. But that 2 is going to come out as a reciprocal. So 2 is going to be carried over, but it's going to come as 1 over 2. Here there is a 4 also, which is going to come as 1 over 4. So which means what we get? So I have a half multiplying these two, so they will cancel each other out. So I just remove the negative. But remember, the integral, of course, is a positive sign, so this becomes only sine 2x. Then here also we've seen we have differentiated. F4 is coming and it comes out as a quarter. So which means I get 1 over 8. So I have 1 over 8. Then cos becomes sine 4x and then plus k. So this gives us the final solution as that. So that's the result of our integration. So every time when you're dealing with powers, these kind of powers, even powers, always use the half angle identities. It's always like that all the time. So let's do now for cos 6x. Let's find what is the integral of cos 6x. So the integral of cos 6x. So they'll say evaluate. So just as I said, the procedure never changes. You see that? So what you do is you take your integral I, and then cos is broken down into powers of 2. So I have cos squared x, cos squared x, cos squared x dx. Then for each cos squared x, I replace with the half angle identity. So I'm going to have half of what? So I'm going to have half of 1 plus cos 2x. You see that? Then again, I'm going to have another one half 1 plus cos 2x, then dot half 1 plus cos 2x, then dx, like that. Then now the three, these half, they multiply half, 1, 4, 1, 8. We take them out, we get 1 over 8 outside. Then we remain with 1 plus cos 2x all cubed dx. Then now what we need is to expand this guy. You see that? So we have to expand this guy. So what is the expansion of this guy? So it's going to be integral of what? So let's expand. So we'll get 1 plus 3 cos 2x plus 3 cos 2x part squared, then plus cos cubed uh, here, here, dx. So this one is a very dangerous problem for now. So because what has popped out now is an odd power has emerged, which we haven't learned. So because there's an odd power that has popped up, we are not going to continue with this question. As the other two were fine, this was fine, this was fine, but now there's an odd. An odd power hasn't been discussed so far, so we're not going to finish off this problem. You're going to learn how to finish it off when you have learned how to deal with odd powers of cos theta and sin theta. But for even powers, this is how we always deal with them. So I'm surprised as to why this one actually didn't work, because most of the time when you're dealing with even powers, your half angle must always give you what you need all the time. So I'm quite surprised as to why now it pops an odd power there. But at least you must be getting the idea as to how we approach what we call these even powers of cos theta and sin theta. So because of that odd power, we'll just put this on hold a bit. And then maybe let's look at another different example to cover for this. So another different example would be evaluate the integral sin squared x cos squared x dx. So how do we deal with this one given now? So this one, again, if you look closely, you will see that it involves even powers of sine and cos. So if sine squared x, cos squared x dx. So it involves those powers. So what we're going to do now is, since both the powers of 2, we're going to replace with half angle. So for sine, it's going to be half 1 minus cos 2x. Then cos squared is going to be half 1 plus cos 2x, then dx. Take the halves outside, they become a quarter after multiplication. And I have 1 minus cos 2x, 1 plus cos 2x dx. Then now what we need is to realize that this thing, it resembles a difference of two squares. So which means if we are to apply it in reverse, we're going to have 1 minus cos squared 2x, then dx, like that. So that's what we have. So now we know that we have an even power there. So we use half angle here. So for that term that is sitting here, we're going to apply the half angle identity. And when we apply the half angle identity, what do we get? So we have 1 quarter, then integral of 1 minus, so this becomes half of bracket 1 plus cos 4x, then dx. Then if you look at these guys, this guy and that guy, these are like terms. Because they are like terms, what we want now is to add them together. And what do we get? So when we add these two together, we'll see that we have 1 quarter integral. So it's 1 minus half. So it's half, then minus half cos 4x, then dx, like that. So what do we get now? So now what we want is to integrate that. So 1/4 is going to wait outside as we integrate. So integrate half, you just get half x. Then here, first you differentiate here, you get 4, which comes out as a quarter. So it's going to be minus 1/8. Then the integral of cos is sine. So when we integrate cos, we get sine. So this gives us sine of 4x, then plus k, like that. So this is how we do an integration of all these even powers. So that's how you deal with even powers. So the next thing that we want now is to learn how to deal with odd powers of sine and cos. So now, odd powers of sine and cos. So we want to learn how to deal with odd powers of sine x and cos x. So how do we integrate odd powers of sine x and cos x? You see that? So to integrate, uh, to evaluate odd powers of cos x or of sine x and cos x, we need the following results. So we need to know the following results. You see, so what are these results? One of the results is that the integral of sine to nx cos x dx is equals to what? So it's going to be 1 over or sine to the power n plus 1 of x over n plus 1 plus k. Then b, we have integral of cos to the power nx sine x dx is equal to what? So it's going to be cos to the n plus 1 x over n plus 1 plus k. Sorry, it's a minus here. It's minus. So these are two results that you should keep in your memory. But if you learn your integration very well, you don't actually need to even memorize these results. So these are results that can be easily found by substitution. You see, so if you can play around with substitution, you can prove them. You see that. So these results that we have here, they can easily proved using substitution. So if you just apply your substitution technique, you can actually prove the truthfulness of these results. But the question is when to use them. So we always bring them into the play every time when I want to integrate an odd or an even power, an odd power of sine x or an odd power of cos x. That's when you bring these results into the foreplay. Otherwise, you always keep them on the side. So now what we're going to do is we're going to look at examples and see how we can actually make use of these results to do the integration. So a typical example that might be given, you might be given something like this. So they will say evaluate. So they will say evaluate the integral. What integral are we evaluating? So they will say maybe let's say sine cubed x dx. So you might be given something like that, and then they say, can you evaluate that integral? So the question is, how do we go about it? So to go about this is how we proceed. You see, so to go about this is how we proceed. So we'll say let I be the given trig. But every time when you are dealing with these odd powers, what you do is you take that odd number and you break it into uh, into sums of twos up until you have exhausted all the possibilities. So what we're going to do is we're going to take sine cubed and break it into powers of 2 and see. So there's only one way to break it as power of 2 is just sine squared x then sine x, like that. You see, so we want to break it powers of 2 such that there is a term in sine x that is an odd power with it. Once we have achieved that, then our focus is now on the square rooted part. So now we don't use the half angle identities anymore. You see that? So here we use cos squared x plus sine squared x is equals to 1. So here now when you're solving this problem, you don't replace signs in the even powers using half angles. Instead, you make use of that identity there. So which means if I were to use that up, I'll get the integral sine squared x. If you make it there, you'll get 1 minus cos squared x, then times sine x, then dx. Then I expand the bracket out. So when I expand the bracket out, I'll get sine x minus cos squared x sine x, then dx. Now it's time to just integrate these guys. So let's integrate these guys and see. So when we integrate these guys, what we get? So when you integrate sine x, you know that the integral of sine x is minus cos x. So here, if you look here, this thing that you have here, it resembles the result that you have written already. Let's go and recheck. You see, you have a product of a cos and a sine. So you have a product of a power of a cos and a sine. And if you look here, you have a product of a power of a cos and a sine. So which means we're going to make use of this result to perform this integral. You see? So which means here, what we're going to have, we know that we're going to have a negative coming, which is going to cancel that one. So we're going to have a 1/3, then cos cubed x, then plus k. So that finishes up the problem. So this is how you deal with even or odd powers of trigonometric functions. So you always deal with them in that manner. You see, so you always deal with them in that manner. So let's see another problem, different one. So what did we integrate here? We integrated sine cube. Let's put cos, a different thing now. So let's put cos 2. So another example will be evaluate the integral of cos to the power of 5x dx. So how do we evaluate that guy there? So same thing, we take the given function and we split it, break it up into powers of 2. So we have cos squared x, then cos x, then dx. Now, for each power of 2 that you have, you use that identity. Cos squared plus sine squared is 1. So using it here, you will get 1 minus sine squared x. Using it there, you get the same thing. So I square that, and then I get cos x dx. Then now I expand the rooted part. So what do I get? So when I expand here, I get 1 minus 2 sine squared x, then plus sine to the power 4x, then cos x dx. Then the next thing that we do now is we take cos x, we expand it inside term by term, like that. So we take it, expand it inside, and what do we get when we expand it inside? We get cos x minus 2 sine squared x cos x plus sine to 4x cos x, then all these integrated with respect to x. So that's what we have. So what we need now is to deal with this. So if you look, the first term is easy. When you integrate cos, you know that you get sine x. Now minus. Now if you look at the second term you have a power of a sine multiplying cos. So we go back to those results. So you have a power of a sine multiplying cos, so you use this result. So you see the answer is sine n plus 1 over n plus 1. So what it simply means is that you add 1 to the power and divide by the nu. So which means here you will get 2/3 sine cubed x. Then here again you will get plus 1/5 sine to the power of 5x. Then you add your integral constant. So this is how we evaluate integrals when you have odd powers. So for odd powers, this is the procedure. So these are the things that you must try and practice more and more frequently up until you have mastered how to do. You see, so these are problems that you have to try and practice and master in integration for trig functions. Then now, what we want is to look at integrals of this form. So integrals of the form um, cos nx sine mx or integral of cos nx cos mx dx. So now what we want is to learn how to deal with integrals of which have this structure. You see that integral of this format, which come in that form, how do we deal with such integrals? So integrals as this can be a bit tricky, but we are going to uh, see how to handle them. You see that? So such integrals are handled. So such integrals are handled using expansions. Such integrals are handled using expansions. So such integrals are handled using expansions as we shall demonstrate. So if you want to deal with such integrals, we make use of expansions uh, for dealing with such things. So now let's see uh, what next, how to practice these kind of problems. So a typical problem that you might be given can be something like this. So they'll say evaluate the integral of cos 5x sine 3x dx. So you might be given something like that, and then they say evaluate that integral there. So how do you deal with an integral like this one? So an integral like this one, you can only deal with them using expansions. So what you do is you have to pick the correct expansion for the problem. You see, you have to pick the correct expansion for the problem, and to pick one, this is how we proceed. So what we do now is this. So first you have to ask yourself, is there an expansion that can actually give you something like this? And you will understand that here, if you look close, you'll see that there's one. Like for example, if you take the expansion of sine 5x plus 3x and expand it, what will you get? You will get sine 5x cos 3x plus cos 5x sine 3x. You see, so I'll call this one. Or if you take sine of 5x minus 3x, what do you get? You will get sine 5x cos 3x minus cos 5x sine 3x 2, like that. So you can see that both these two expansions, they have the term that we need. So what we want to remain with is we want this guy, because this is the guy in our integral. So this is the required guy there. You see, so this is the guy that is in our integral. So we see that that guy, if we can manufacture it out, it's exactly what we need. So how can we keep that guy in these two equations that we have? So in these two equations that we have, in order to keep that guy present, I just have to take these two equations and subtract them. You see that? So now if I take maybe equation 1 and I subtract equation 2, what does it mean? So you see, this guy is going to subtract this guy, which means sine of 8x is going to subtract sine of 2x, and these guys, they are going to cancel each other out. So this guy and this guy will cancel, and I'll have this guy subtracting that guy. So I'll have 2 times of cos 5x plus sine 3x. So which means now we have created, sorry, it's not plus, cos 5x sine 3x. So what we need now is to make this guy, our subject. So now what we realize, so we see that cos 5x sine 3x is just half of sine 8x minus sine 2x, like that. So what we do now is we can take this guy and plug it back into our integral, because that's what we're integrating. So therefore, what is I? So therefore, the integral I that we're evaluating is just half of the integral of sine 8x minus sine 2x, then dx, like that. And what do we get? So we have half of what? So when you integrate sine 8x, what do you get? So remember, first you differentiate 8x, you get 8, you take out as a reciprocal, you get 1 over 8. And what is the integral of sine? It's minus cos, so you get cos 8x. Then here again, same thing, differentiate there, you get 2, take it out, it becomes half. So you get a half coming. But now when you differentiate, integrate sine, you get minus, so you get a plus cos 2x, then plus k. Then now you can multiply the half outside, so you get minus 1 over 16 cos 8x plus 1 over 4 cos 2x, then plus k, like that. So this is how we get to handle integrals of this sort, you see. So let's do one extra example again to practice more of this guy. So another example will be evaluate now the integral cos 10x cos of 3x dx. So you'll be given something like that. So now you've seen the logic behind which we solve these problems. So how do we answer such problems? So to answer such problems, we now know the story. We choose an identity that will produce that. So we see that definitely the best identity to look for is for cos. So first I look at cos 10x plus 3x. What does that give me? Cos 10x plus 3x will give me cos 10x cos 3x minus sine 10x sine 3x. That's what I'll get. So I'll call this 1. Also, similarly, if I have 10x minus 3x, what will I get? So I'll get cos 10x cos 3x, then plus sine 10x sine 3x, then 2, like that. Then now what I do is I take 1 and I add 2. And what does that give me? So when I add these two guys, at the first one is going to be cos of 13x plus cos of 7x. And what does it give us? So it gives us 2 cos 10x cos 3x, like that. You see? So now this is our guy that we need. So if you look, this is what we need. Because this guy resembles perfectly what we have in our integral. So now we see that if I divide by 2, I get. So therefore, now what is the integral I? So therefore, the integral I that we are looking for is going to be half integral of cos 13x plus cos of 7x, all these with respect to x. So what we get then here? So what we get here now is half is going to be weighting, and we deal with that. So here you differentiate, take out as a reciprocal, so you have 1 over 13, cos gives us sine 13x, then again here you have 1 over 7, then sine 7x, then plus k. So therefore, what is the final answer? So the final answer then becomes half, sorry, so multiply by half now, so we have 1 over 26 sine 13x plus 1 over 14 sine 7x, then plus k. That finishes off our final answer. So yeah, this is how we deal with the integration of trigonometric functions. And that's all for now that you have to know, though later we're going to encounter them as we make use of them in substitutions and stuff. But for the integration of trigonometric functions, that's the whole theory that lies behind it. So once you master this, now you can integrate all trigonometric functions with ease. So let's end it here.